Welcome to the next session, my dear friends. So in the previous session we were discussing about the design of under drainage system, and now in this session we are starting, see, during the backwashing how the filter media will change and how to prevent the filter media from getting damaged while during backwashing. So how to design all these things, what happens exactly in the filter media during the backwashing process and all, we will learn in this session. So I already told you, so the backwashing should be done such that it will remove only the impurities, not the filter media particles. Now here, if you look at the filter media particle, generally on this filter media particle there will be gravitational force which is acting downwards, okay, gravitational force which is acting downwards as we are applying force of backwash or velocity of the backwash on this particle, okay. So that means this particle is kept in a fluid. Okay, when you are sending some water in the upward direction, that means this particle is having some thrust by the water in the opposite direction. Generally in our fluid mechanics terminology we call that as the buoyancy force. Whatever the thrust that a water will give on a particle, we call it as buoyancy force, okay. For a while we will discuss some kind of fluid mechanics concepts, okay. For a while we will discuss this matter in terms of fluid mechanics, because we wanted to be the filter media hydraulically stable. So because here we are dealing with water, right? So during the backwashing we are sending water with very high velocity or with some high pressure. So that is why we need to safeguard the filter media from that high velocity, high pressure water. So that is why we need to use some fluid mechanics concepts here. So whenever we are applying that kind of pressure from the bottom, then it causes a buoyancy force inside the material, okay, and I am analyzing this for single material and then I will apply this concept to the whole material. So if I take single sand particle, there will be some weight of the single sand particle and there will be buoyancy force of single sand particle. So this is buoyancy force. Okay, so buoyancy force. Here the buoyancy force, generally what is the value of buoyancy force? It is equal to volume of the solid, okay, it is equal to volume of the solid into volume of specific weight of water or any fluid in which it is. Here it is water, that is why the volume of solid into gamma W, okay. So the weight of the material is volume of the solid into gamma of solid. This is weight and this is buoyancy force. The difference, whatever is the difference, so that much force it can take, isn't it? So the difference of buoyancy and the gravity force is the force which we can apply in this opposite direction. Are you able to understand what I am saying? So the net force on the particle here, net force on the particle is how much? Fg minus Fb, which is equal to, so Vs to gamma S minus gamma W. So this is the net force on the particle from particle point of view, particle perspective. So from particle perspective, this is the net force on the particle. If I take a group of particles together, so if I am taking group of particles together, so this is the group of particles, that is media, bed. This is the group of particles. On this group of particles, so the same thing, the net force we can identify from pressure point of view. So because of this increase of this, I told you already, increase of this velocity or increase of this compressed air pressure, it will cause some thrust on the filter media bed. Let us take this as pressure which is generated on the filter media bed because of this backwashing, that it is P1, and this P1 is caused by water. P1 is caused by water. So the P1 is nothing but, so gamma W into H1. Let us take that P1 at the beginning, at the bottom of the sand bed is gamma W H1, and P2 at the exit point of the sand media, this is sand media or filter media, it is taken as P2 and it is equal to gamma W into H2. Okay. So from the point of view of this, from the point of view of pressure, from pressure point of view, from pressure point of view, the net force is equal to P1 minus P2 into area. Pressure is nothing but a stress. Pressure is nothing but stress. So that is why we need to take it as P1 minus P2 into area. So that is equal to gamma W into H1 minus H2 into area. So H1 minus H2 is nothing but head loss. So the head loss that is occurring when the water is traveled from this end to that end, that is nothing but HL. Okay. So then it is gamma W HL into A. Area is nothing but, see what is the area we need to take here. So it is not needed to take area. Let us keep it aside for a while. So this is nothing but the net force. This is nothing but the net force, right? So here this is again net force. This is again net force. This net force is from particle point of view. This net force is pressure point of view. Both are acting on the same location. So these two are equal. So 1 is equal to 2. So 1 is equal to 2 because both are net forces only and both are acting at the same location, but we have calculated from two different perspectives. One is from the particle perspective, another one is from point pressure perspective. That means as a whole, if you are taking a media, that means these two are equal. So 1 is equal to 2. 1 is equal to 2. That means volume of solids gamma S minus gamma W is equal to gamma W HL into area. So this I can write it as area. So if I am taking this volume of solids, as this is for one particle, this is for one particle. If I take all the group of particles together, then that will be, instead of volume of solids, then we will get the total volume of solids here. Total volume of solids. So total volume of solids is nothing but the area into Z, thickness. Area into Z. Okay, so here volume of solids I want, right? Volume of solids I want. We need to go back to the soil mechanics concept here again. We need to go back to the soil mechanics concept here. So we need volume of solids. If this is the, so if you know the porosity of the sand media, if you know the porosity of the sand media, so this is sand media, this is sand media. So let the porosity is N, which is equal to volume of voids by volume of soil. Volume of soil. Volume of soil means area into Z. Okay. Let this is Z. And 1 minus porosity is equal to volume of solids by volume of soil. That means 1 minus porosity means what? So 1 minus volume of voids by volume of soil. So that means when you take this volume of soil minus volume of voids is nothing but volume of solids. That is nothing but volume of solids, right? So here volume of solids is equal to volume of the soil into 1 minus N. Volume of the soil into 1 minus N. So take this here. So volume of solids is nothing but volume of soil into 1 minus N into gamma S minus gamma W is equal to gamma W HL into A. The volume of the soil is nothing but area of the soil into Z. Okay, to 1 minus N. So if you take this gamma S, gamma W common, then gamma S by gamma W minus 1 is equal to gamma W HL A. So A gets cancelled, gamma W gets cancelled. So HL is equal to Z into 1 minus N into Z minus 1. Okay. HL is equal to Z into 1 minus N into Z minus 1. See, one more point. Again, listen carefully whatever I am saying. So we have arrived this equation. We have arrived this equation by two things. One is when a single particle, if you look at a single particle, on this single particle, when there is no water, nothing, then on this particle there will be only gravitational force, right? There will be only gravitational force. When you send water from the bottom, so for backwashing, that water will exert some pressure, some thrust on a particle, that we call it as buoyancy. So that is nothing but buoyancy. From here we have found the net force on the particle. We have found the net force on the particle. Similarly, this net force, why we are calculating net force from buoyancy point of view is, you may have a doubt. Sir, buoyancy is when the water is stationary, whatever be the force exerting by the thrust of water, which is a thrust. Generally, moving water will exert different pressure, right? Moving water will exert different pressure. If the water is at rest, so fluid static, when fluid is static, then it will exert a buoyancy force. Okay, assume, so this buoyancy force when exerted on the particle, or if you take a small ball, you drop it on the water and it is under static water, so that will exerting a buoyancy force. So because of that buoyancy force, the ball is not moving downwards or not going upwards, it is also in static mode, right? Here also our intention is, we want to keep this particle in static mode, we don't want it to go away. So that is why this criteria will help the particle to sustain in the filter media. The velocity of backwashing should be such that the buoyancy, this buoyancy, so the force which is coming out of the backwashing pressure should not increase, should not be more than this buoyancy pressure. If it is more than this buoyancy pressure, then the particle will go away. That is why this thing is the pressure which we are exerting. This calculation which we are doing in the second equation is from the pressure which we are giving from the outside, and this we are calculating from the capacity of the particle. If you look at this point, we are not considering the velocity of backwashing, we are not considering the pressure of backwashing, we are considering the capacity of the particle. Everywhere we are taking the particle property, volume of solid, gamma of solid, gamma of W. Here on the right hand side, if you look, this is the head of the water, and this head of the water will be kept such that it should not be more than the buoyancy force of the particle. So this is the capping, this is the limit, and we are equating the head loss or pressure driving head to this limit such that this head loss should not be more than this buoyancy. Are you getting my point? So this thing is the pressure which we are giving, and this is the capacity of the particle. So this capacity, the head loss should be such that it should not exceed the capacity of withstanding of the particle. That is why we have equated these two, and by equating these two we have found the head loss. And generally the buoyancy force is always constant when the volume is constant. So because the buoyancy force is defined as volume of the solid and the gamma of water. So before filtration and during backwashing, we are having the same filter media. Same filter media will have same amount of sand particles. That means the volume of the solids before and during backwashing and even after backwashing are same. So here, so the volume of solids Vs is constant before and during and after backwashing. Right. So this is same. This will not change. That means this will not change because we are assuming that no particle is being removed. That is what is our design. Why we are doing this much of analysis and all is to protect the filter media. That means we don't want to lose any of the volume of the solid after backwashing or during backwashing, right? So that means, so we assume that volume of solids is constant. Volume of solid if constant, then buoyancy force is constant. Then this buoyancy force is constant and area is also constant. We are not changing, we are not expanding the filter media area before and after. So this is also constant. That means if you see this term, the whole term is constant. That means HL is also constant. The head loss, even the bed is expanded. This head loss should be constant. Because if you look at this, Vs is constant, gamma S is constant, gamma W is constant, area of the filter is constant. We cannot increase the area of the filter during the backwashing. Only thing which is changing during the backwashing is this bed will expand. So the depth of the bed will expand. That is the only change that will happen during the backwashing. So that means every other factor is same, then HL is also constant. So head loss is constant during the backwashing. HL is constant during backwashing. Right? Now, if the bed is expanded, because of this thrust from the bottom, so the bed has expanded like this. So this is expanded bed thickness, and earlier the bed is having porosity N. Now the expanded bed porosity is Ne. So the same head loss can be written like this also. Now for the second case, with expanded thickness and expanded porosity, expanded bed porosity, then it is Ze 1 minus Ne into Z minus 1. Z is a constant value, that is specific gravity of the particle will not change. So as HL is constant now, so if this is 1 and this is 2. So we can equate 1 and 2. So 1 is equal to 2 as HL is constant, as head loss is constant during the backwashing process. That means, so ZE Z into 1 minus N into Z minus 1 is equal to ZE into 1 minus NE into Z minus 1. So this is the equation which will help you to find the expanded bed thickness and expanded bed porosity if you know any of them. Okay, if you know the rest of the data, we can find easily 1 minus N is equal to ZE into 1 minus NE, where Z is the original filter media thickness, ZE is expanded bed thickness, and N is porosity of original filter media, and Ne is expanded bed porosity. Ne is expanded bed porosity. So from these values, if you know the original bed properties and the expanded bed property, any one of them, either expanded bed porosity or expanded bed thickness, we can find the other. Okay, so from this what we can find? What should be the pressure? That first thing we will know on the particle, and the second thing is what would be the expanded bed thickness, because I told you that expanded bed thickness should not surpass 50% of the depth, 50% of the Z it should not surpass, otherwise what happens? So though it is not moving out due to backwashing, it will move out because lack of support. So we are having a wash water trough up to D/2 only. If there is no support, then what happens? Whatever the sand which is being expanded will go out because lack of support on the lateral directions, on the sides. If there are no side wall, then it cannot stand. Okay, now here so generally how to determine this velocity of backwashing? So far we have discussed the force of backwashing and head loss of backwashing. How to define the velocity of the backwashing? See, the expanded bed porosity depends on settling velocity of the particle. The expanded bed porosity depends on the settling velocity of the particle. How it depends on the settling velocity of the particle, let us see. So why do we need this expansion of bed generally? So what is the necessary to expand this bed? So why we need to expand the bed is, so in order to wash the sand media, we need to increase the void spaces. So without increasing the void spaces, how can you clean the impurity? That means we want to expose all the surface of the filter media. So the filter media, if you take a filter media particle like this, so earlier the filter media is like this. Now if you don't expand it, how can you get complete surface area into your control to wash? So to get all the surface area to get exposed, we want to separate them like this. We want to expand it. If we don't expand the bed, then the wash water cannot clean these locations. The wash water cannot clean the locations where it is having contact with the other particles. So to remove the contact between the particles, we want to expand the bed. What is the necessity of expansion of bed is to have a full access to the surface of the filter media particle, so that we can clean all the filter media clearly. That is why we need the expansion of bed. We need the expansion of bed. So the expanded bed porosity depends on the settling velocity of the particle and velocity of backwash. See here the expanded bed porosity depends on two things. One is settling velocity of the particle and velocity of the backwashing, because here expanded bed porosity is not affected by head loss. It is not affected by head loss. Whatever the head loss we are keeping is constant before and after the operation of backwashing. That is why, so this porosity depends on the settling velocity of the particle and backwashing. Settling velocity means the particle which is having a tendency to come down. This is settling velocity. And another thing which we are applying on the same particle is velocity of backwashing. So these two, which is more, in that direction the particle will move. If the velocity of backwash is more, then it will move up. The settling velocity is more, then it will come down. So the particle movement is decided by the backwashing velocity and the settling velocity of the particle. So that is why the expanded bed porosity is a function of settling velocity and velocity of backwashing. Settling velocity and velocity of backwashing. So that is given empirically like this. Empirically, the expanded bed porosity is given as Vb by Vs whole to the power of 0.22. Vb by Vs whole to the power of 0.22. This is the expanded bed porosity value given. Actually, during the backwashing, the velocity is very high. Okay, the velocity is very high, causes the flow transitional. The velocity is very high, makes the flow no more laminar. That means the flow of backwash is nearly transitional. The flow of water during backwashing is nearly transitional. Not turbulent, but it is transitional. If you don't create transitional flow, so if you are washing anything, you will put it in water and stir it like this. If you slowly send that particle into the water and slowly remove the particle from the water, will the dust removed from the particle? No, no. So generally, if you want to remove any dust from the particle, we will insert it in water, we will just shake it or do some kind of transitional thing, turbulent thing. Otherwise, the impurities will not get removed out of the sand particles. So that is why generally during the backwashing, so the flow is now no more laminar, it will be transitional. But generally, as far as gate examination is concerned, so we used to take the settling velocity as it is in laminar only. That means here also we use the same formula of Stokes law. So generally Stokes law is not applicable in transitional flows. Stokes law is applicable only for laminar flow. So that is when exactly during backwashing there will be transitional flow. So during transitional flow, the settling velocity is defined like this. Vs is equal to square root of 4 by 3 G square root of 4 by 3 g into d into g minus 1. 4 by 3 g d into g minus 1 by cd, coefficient of drag. So this is the exact formula of settling velocity. Settling velocity, where g is acceleration due to gravity, g is gravitational acceleration, g is gravitational acceleration, and d is the diameter of the particle, d is the diameter of the particle, and g is specific gravity, and cd is coefficient of drag, which is equal to, cd is coefficient of drag, which is equal to 24 by re. Generally for laminar flow, when re is less than 1, generally we don't take this here. It is transitional flow, we don't take this here, but cd is equal to 24 by re plus 3 by square root of re plus 0.34 when re greater than 1. That is for transitional flow. So generally we need to take this re here, we need to take this re here, this cd here, okay, this cd here, and if in case re Reynolds number is not given, cd is not given, generally for engineering services this formula is needed, okay. So if it is gate examination, majorly in gate examination they are taking Vs as settling velocity of Stokes law, okay. This is the settling velocity for actually transitional flow will exist, and for transitional flow this is the settling velocity, and cd for the transitional flow is this, okay. So if the Reynolds number is not we don't find Reynolds number in the question, or if you don't find the coefficient of drag in the question, then we cannot use this formula. That means the examiner is indirectly saying that take laminar flow formula only and do the question. That is indirect indication, okay. If it is given, cd is given, then don't prefer the Stokes law equation. If cd is given, then prefer this equation to find the Vs, okay. If you know the Vs, and how to find Vb, let us see how to find Vb, because Vs and Vb both are needed to find the expanded bed porosity. So Vs, another formula is also there. This is one formula, exact formula, but generally in gate examination, settling velocity we also take it as the Stokes law settling velocity only. So that formula you are all aware of. Anyways, I will write that formula also here for just understanding. So Vs, if coefficient of drag and re is not given, then take Vs as z by 18 s minus 1 d square by nu, or g into rho s minus rho w d square by 18 mu. So this formula you all know already. So now this formula also we apply. This also apply where in case of re and d, cd is not there in the question. And we need to find the rate of backwashing, this Vb. So Vb is nothing but velocity of backwashing or rate of backwashing. So which is equal to, if you know the quantity of backwashing water, the discharge of backwashing water, then discharge of backwashing by the plan area, discharge of backwashing by plan area. This is also velocity of backwash, this is also velocity of backwash, or else there is another formula for VB. VB is equal to Vs into Ne whole to the power of 4.5. See, simply this formula is converted like this. So if you take Vs here and Ne this side, so this is another formula. So Vs into Ne whole to the power of 4.5. So but this formula we can use only if you know the expanded bed porosity. To find expanded bed porosity, you need backwashing discharge by plan area, then we will get the velocity of backwashing. So this is all about the backwashing. And its effects on the filter media. So now, to find the head loss in the filter media, okay, there are some formulas to find the head loss inside the filter media. So those formulas are not that important for GATE, but we don't know. They may even ask sometimes. So that is why let us discuss those formulas also. Head loss during filtration. Head loss during filtration given by Karaman-Khojni equation. She is called Karaman-Khojni equation. So HF is equal to FL V square. You might have learned this in your fluid mechanics. FL V square by GD into 1 minus N by N cube. These are all empirical formulas. Okay, we need to by heart them along with the what are the terms given. F is equal to 150 into 1 minus N. 150 into 1 minus N by Re plus 1.75. And Re is equal to rho W V into D by mu, Vd by mu, or it is equal to Vd phi by nu. So this is the formula. So let us discuss each and every term here. Here F is friction factor. F is nothing but the friction factor. F is friction factor or friction coefficient, and L is the length. V is velocity. N is porosity. Re is Reynolds number. Phi is shape factor. Mu is viscosity, dynamic. And nu is kinematic viscosity. So these are the, see here length is nothing but depth of filter media. That is L is equal to Z. L is equal to Z, length of the filter media that where the water is traveling. And here V is the velocity, that is superficial velocity, that is nothing but rate of filtration. So velocity is superficial velocity, or rate of filtration. Simply superficial velocity is nothing but rate of filtration. Porosity of filter media, porosity of the filter media, and phi is the shape factor and d is the diameter of the sand grains. So d I haven't told. D is the diameter of sand grains. So this is the formula, not needed for GATE examination. But if you are having so much of time, if you have studied everything, if you are aiming at a top rank less than 10, then I prefer you to remember this formula also. So next is particle removal efficiency of filtration. Particle removal efficiency of filtration. Particle removal efficiency of particle removal efficiency of filtration. So here, there is a filter media like this. For example, let us take a filter media like this. So into this filter media, some concentration C0. So impurities are there. C0 is the concentration of incoming impurities is there. At some time t, so the concentration of impurities coming out of the filter media, let it is CT. Let it is CT. Then the particle removal efficiency is nothing but C0 minus CT by C0 into 100 at a particular time, isn't it? The particle removal efficiency is equal to C0 minus CT, where C0 is concentration of impurities in incoming water. CT is concentration of impurities at any point of time, t. At any point of time t. Okay, that is CT. Then the efficiency of the filter is C0 minus CT by C0 into 100. So there will be a term called Iwasaki-Isaku equation for filters. Iwasaki and Isaku equation of filters. So let us see what is that equation. See here, if you take a small part of depth of the filter media which is having a depth of dz, let us take a small part of filter media, that is dz, and this dz is removing a particle concentration of dc. Okay, so let dz is a small component of filter media removing dc of impurity concentration. Okay, then the rate of removal, that is dc by dz. So that dc by dz is proportional to the concentration of impurities present inside the water. If the concentration is more, then the more impurities will be removed by unit depth of filter. And if the concentrations are less, concentration of the impurity is less, then less amount of impurities are removed in the filter media. So if you take this with a proportionality constant, so dc by dz is equal to minus I into C, because why minus? As I told you, concentration is decreasing, removal is happening. If addition is happening, then it is positive. Removal is happening, then it is negative. Okay. So now if I want to take this, so dc by C is equal to minus I dz. If I take it with time, so with the time, initially it is C naught, or after some time it is Ct, and the depth 0 to z. For the whole depth I am finding for this duration. Okay, for this duration, for the whole depth I am finding the removal of impurity. Then it is ln C naught Ct is the limit, is equal to minus I into z. Okay, now this will become ln Ct by C naught. This will become ln Ct minus ln C naught, that is equal to ln Ct by C naught, is equal to minus Iz. Okay, minus Iz. Now, so this I is nothing but 1 by z. So this z will go here, ln C naught by Ct. This I is equal to 1 by z ln C naught by Ct. So this is called filter constant. I is called the Iwasaku-Issaku constant, is nothing but filter constant. This is called filter constant. Now here I can rearrange these terms. So I can write it like this. So from here, if you come here, so this is equal to 1 minus Ct by C naught into 100. I can write this efficiency as C naught by C naught minus Ct by C naught into 100. Okay. Now here so this is efficiency in percentage. So efficiency in percentage by 100 is equal to 1 minus Ct by C naught. Okay. So Ct by C naught, if I bring this here, that implies Ct by C naught is equal to 1 minus efficiency in percentage by 100. Okay, that means here 100 minus efficiency percentage by 100. Okay, so this is Ct by C naught. So Ct by C naught. So Ct by C naught is equal to Ct by C naught is equal to Ct by C0 is equal to 100 minus efficiency by 100. 100 minus efficiency by 100. It implies C0 by Ct is equal to C0 by Ct is equal to 100 percentage by 100 minus efficiency percentage. So C0 by Ct is equal to 100 percentage by 100 minus n. Okay, here this is 100 minus efficiency, 100 minus efficiency. Okay, so now I can replace this C0 by Ct. Here I can replace C0 by Ct by this. C0 by Ct by this. That means I, filter constant, is equal to 1 by depth of the filter ln 100 by 100 minus efficiency. 100 by 100 minus efficiency. The filter constant we can find using simply the efficiency. If you know, then we can find filter constant. So filter constant is equal to so as per Iwasaki-Isaku equation, the filter constant I is equal to 1 by Z ln C0 by Ct, or which is equal to 1 by Z ln 100 by 100 minus efficiency. Very important formula for gate. Already it was being asked in the gate from this formula. Okay, so this is the formula, very important. Filter constant. Okay, now in the so I will conclude this session. In the next session we are going to discuss what is the effect of filter specification on particle breakthrough. So what is meant by particle breakthrough and what is meant by time for reaching terminal velocity. These things we will discuss, and also we have to discuss the design of filter. So we have discussed the under drainage design, but we haven't discussed yet the filter design. We will discuss the filter design and we will establish a comparison between the slow sand filter, rapid sand filter, and many things are yet to learn. So we will discuss them in the next session. Thank you so much.